Hello, in this video I will show how I designed this board using very little manual editing and a bit of scripting. This design is a ring light where here I have a number of LEDs, and here on the sides I have some mounting holes that enable me to take multiple of these PCBs, connect them together to form a ring. The way that I'm designing the ring is actually in Fusion 360. Here is the basic design, and in Fusion 360 I can also model that it becomes a ring to ensure that the mounting holes are in the right spots, that everything will come together nicely. Also, it enables me to draw some of these other structures a little easier than it would be in kicad. So for example, I am able to lay out the placements of the LEDs in a nice ring so they can also look kind of nice. I have my power rails here. Let's turn off the LEDs there. I have the power rails drawn. In the middle I have ground. On the edges here I have power and power again. So the next PCB will connect to here. Additionally, I have a solder mask here along the edges, so there's a triangle here. Let's see if we can make that a bit more visible. There. So a solder mask enables me to solder adjacent boards together, as well as having them connected via these mounting holes. Additionally, I have cross rail. So this power rail is in the back of the design. On the front, I have the other orientation. So as you can see, on the front, I have power going sort of a vertical, diagonal type of direction. So here we have power is on the left and ground is on the right. Here we see that, let's turn off the masks. Here we see that we have on the bottom here the power rail, and in the middle we have the ground, and then on the top we have power. And again, all of this was drawn in Fusion 360. Additionally, if we unfill the zones, because these power rails are just zones, if we unfill the zones, fair amount of routing, we have vias here as well on each of the pads, which also will help to get some heat away from the LEDs. I have some zone fill vias here to be able to connect the front and back power rails. All of this is done, almost all of this is done in scripting. From start to finish, once you have the scripts in place, it's maybe a half hour of actual wall clock time to get this design done. So in this video, I will demonstrate each of the scripts, but I will not yet describe how they work. That will be in a separate video. So let's get started. I'll start with a blank slate. Here I have the schematic. It's fairly uninteresting schematic. It's simply 3 LEDs in series. These will be powered by a constant voltage supply, topping out at 12 volts, but I'll also have a step-down converter to enable less than that. In my experiments, I found that these LEDs draw about a third of their rated power at 12 volts, and even that is fairly bright. If I were to crank up the voltage even further, the power consumption goes up, but the light emission as measured by my light meter does not go up linearly with that. So driving them not so hard actually shows more efficiency. So it's a total of 60 LEDs in this configuration. So let's go to pcbnew. Okay, so I'm starting with an empty design. First thing, of course, we need to do is import the netlist, and here we have all of our LEDs. One thing that I don't really like about kicad, I believe it is that the placement that you get here is fairly random, and there's a lot of crossover, and trying to move them into place would really be a chore. So the first piece of automation is a plugin that I wrote that takes the schematic placement and it applies it to your PCB. Now I know what is what, and also the ordering of the LEDs makes sense, at least relative to the design that I made. All right, let's move this to the side. How do I get the LEDs to match this orientation? Well, here comes the first scripting task. So here we have a sketch that contains the outlines of all of the LEDs. So for that, I will export the DXF, save as DXF here, and then I save it to the file. I've already saved it, so I won't do that. Coming back into PCBnew, PCBnew actually does have an import DXF file feature. Import DXF works for what it is, but I find that there is a number of disadvantages. For example, when you hit OK here, I want to place it at the center of the page. Okay, fine. I do OK. And the first thing that does is it follows my cursor. Okay, well, if I have several layers that I need to overlay, how do I get them to be exactly in the right spot? So instead, first scripting task that I want to do is to import the DXF onto a layer within pcbnew. To make DXF import possible, I put together a library that will read the DXF file, and then it will walk through all of the polygons, calling a callback to a particular action, set of actions. So in this case, what I want to do is simply traverse the DXF, and whenever it finds a polygon, for it to call a callback within segment actions, which in this case says I simply want to put a polygon onto this layer. Okay, so this is a script that we'll come back to several times. Here we'll turn on the first step, and let's run the script. Okay, so now we have on the comments user layer, we have each of the rectangles from Fusion 360. At this point, the next step would be to move each of the LEDs into place. Now here you'll see that the orientation of the LEDs is not actually what we had hoped for. So we could go into the edit properties mode here and tell it, hey, I want some other rotation. But what is that rotation? And in this design, that angle is not constant. As it goes around the circle, you'll have a increment. So I have a better way. So what I need to do first is at least bring each of the LEDs here into the proper position. In order for the script to work, I need each of the LEDs to have its center point be somewhere within the polygon. It doesn't need to be centered, but it does need to overlap. The center point needs to overlap the polygon. So here you'll see that I've moved all of the devices into place, at least so that the center point of each device is overlapping with the placements that we just loaded. All right, so now the next step is to actually orient the devices the way we want. Let's go back to our recipe. We don't need to load in the placements anymore. Now what we want to do is do an orient action. And I will explain each of these functions in separate videos. The traverse be described, traverse graphics. In this case, you can either read it from graphics you already have on the screen, or you can read the DXF again. So in this case, I am going to turn on the orientation part. Any object of a footprint of this LED 5730 will be affected. So let's go ahead and run that now. Running the same script again, different options turned on, and here you'll see now that each of the devices has been oriented properly. The way that it works is that for each polygon that it finds, it looks to see, is there a footprint of the particular footprint type whose center point is within that polygon? If so, it looks for the longest edge on the polygon, and then it orients the device to be the same direction. So now I have the devices basically where I want them to be. I see here that I have power going along the bottom. I have ground going along here. Since we have 3 LEDs in series, 1, 2, 3, 1, 2, 3, these are all aligned. So these are all the way that I want them to be. I will have power rails along the bottom and top, and ground in the middle. So those will all basically connect themselves. The 4 exceptions to this are this one here, for example. The ground here is on the top, but because the power rail here is along the top here, I would need to route through here to get to it. So instead, I simply rotate it so that now these 2 grounds are adjacent. The bottom power rail goes along here. So it's a simple wired to wire connection here. I need to do that 4 times in this design. Rotate, 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 and rotate, rotate. Now I have the placement that I want. Okay, now let's work on the actual power rails. So in Fusion 360, I have here the back layer. I have ground in the middle, power here on the bottom, power on the top. Additionally, I have a small area of ground here because this is where the actual wire connections will be to the board. Again, I save as DXF. I do the same thing for this as well as for what I call the cross rails. So in this case, I have on the left here, I have power. On the right, I have ground. This ground here will extend to the left to enable connection with adjacent PCBs, as well as the power one here on the bottom. This is the front layer of the PCB. Coming back into KiCad, once again, I come to my recipe script, turn off LED orientation. Now I will call traverse TXF again, and the action in this case will be a zone action, saying, hey, I want to create a zone for each of the polygons that you find on the back layer for power rails. Let's turn that on. And the front layer for the cross rails. And while we're at it, let's also add the boundary of the entire design. Okay, save that again, come back into our scripting console, run that again. So now we have some zones. We fill them. Not everything will fill. The front stuff, of course, will fill because there are the LEDs. For the bottom layer, we don't yet have anything really to fill, right? But again, we'll see that power here goes to the left on the bottom, and then ground goes above that as well on both sides, left and right. So, but at this point, the script doesn't know which nets each of these zones should connect to. So by default, it just puts everything on ground. So we need to change that. So here, this zone needs to be on +12. This zone needs to be on +12. This top zone also needs to be. Now for this top zone, one thing that I found is a little weird is that Fusion 360 sometimes will give me 2 polygons when I really only wanted 1. I imagine that I actually drew 2 polygons in there somehow. So for that, I will simply take one of them and delete it, and I am left with 1 that I can then change to power. Also here on the other side, we have the front copper needs to also be +12. All right. So now let's start making some connection. So because this is a LED board and it will dissipate a fair amount of heat, the way that I want to connect the LEDs to the top and bottom power rails is by having vias for each of these power areas. That will help make the connection to the back layer a bit more robust, thereby helping to dissipate some of the heat. So let's see, how do I do that? Now we could just use this thing here, but then I would like, now in this case, I would like them to be centered. Now I could use gridding, but the problem with that is because I'm on an arc here, sort of a polar coordinate system, there's not really a grid that has the center points in the right spots. Additionally, there's an awful lot of these. For each of the LEDs, well, there's a total of 60, 2/3 of which are power, and each of those has 1 or 2 connections. So again, let's do some scripting. Here what I have is I go through each of the modules for each of the pads. If that pad is one of the net codes that I want, power or ground, then I simply put a via in that location. Fairly simple. I've already talked about this on my blog. So let's run it. Coming back again to the scripting console, I have my ground vias script here ready to go. And so we can see that now I have vias in all the right places. They're nicely centered on each of the ground and power pins. Easy peasy. And at this point, I can also do zone fill, and everything will fill. The one exception here is this ground connection zone here, which will be connected shortly. All right, so now we have a whole bunch of nets that need to be connected. Now I could use the point-to-point router, click here, but I found that especially on the sort of non-45-degree placements, getting it to actually route the way I want is tricky. I've tried all of the different options that are available in the preferences menus, and what I really want is just a wire from here to here, a wire from here to here. Also, even if it's possible to do it with the point-to-point router, there's 60 of these LEDs. It's a lot of work. There's a lot of clicking. Me, I prefer to do scripting. So for that, I have a script that will generate the minimum spanning tree of all of the nodes within a net, and it will blindly make point-to-point connections between those. It does not try to do any obstacle avoidance. It doesn't try to be fancy in any of those ways. So it's certainly not a general purpose router, but in this case, it does the job. Let me show you how it works. So here I have a script. I call it Delaunay because it generates the minimum spanning tree based off of a Delaunay triangulation of the points, which may be interesting, but you probably don't care about. The part that I do want to maybe highlight a little bit is that the SciPy is a nice library that provides a lot of routines for computing things like minimum spanning trees and Delaunay triangulations. And you see here, the script is not very long. First, what I do is I connect which connection points are for each net. So I have a dictionary here of nets, and the nets then is populated with all of the pads in that net. I then compute the Delaunay triangulation and the minimum spanning tree. The Delaunay part in this case is not actually necessary because minimum spanning tree, if I just give a complete graph, meaning every node connects to every other node, minimum spanning tree will pick out of that complete graph the best set that you need to actually connect everything. So let's run it. Here we are again in the Python shell, ready to run it. So here we see that all of the nets have been routed. But one thing I forgot to do is to change the widths of the nets. I want something a little thicker than the minimum wire size needed. Come in here, change the track width to be double the default, global deletion, remove all tracks, but we don't want to get rid of the vias that we just put. So let's try that again. Once again, run the script. Now we have thicker wires. Great. Now, this routing is pretty close. we have my direct connection between the adjacent nets. I have my within these two pads, which are internally connected in the LED. But because it does not do obstacle avoidance or anything like that, I have things like this. So I need to do a little bit of cleanup. So we'll get rid of the wires here along the bottom. And if we do zone fill now, we'll see that these power rails are now broken up a bit. So see here, I have this ground, which while it's legal, messes up my connection between the top here and the bottom. So let's unfill the zones and let's get rid of some of these guys as well. I'm actually deleting a little bit more than I need to. The reason why is that a via fill script that I have later, which does actually take into account obstacles, won't work as effectively if I happen to have these wires. Here's the routing I have left over. It's a lot easier to delete stuff than it is to put it there in the first place. Filling again, we'll see that we have zones that are much more contiguous. We're now able to connect from the bottom here up to the top. All right, so now that I have the routing between the LEDs, and now that I have the power supply, let's see if we can make the power grid a bit more robust. I have a lot of areas here between where I really want to connect between the two layers a bit more, so between these LEDs. So for that, I have another script. This script I will describe in another video, but as a short synopsis, it uses another very nice library out there, Shapely, which does a lot of geometric operations for you. It enables you to merge polygons, shrink polygons, things like that. So basically what I do is I find the intersection of the top and bottom power rails for each of the nets. From that, I subtract the existing routing and vias. I subtract the LED footprints. So all the portions of the polygon that are left over are places where I can put a via. And finally here at the end, that's what I do. Let's run the script. Here we are back in the Python shell, and now we have a bunch of vias connecting the upper and bottom layers of the power grid. So here we see that I have power rail along the bottom and power on the left. So they're connecting here as well as here along the top. In the middle, I have ground, and I have ground on the right. A very robust set of vias. Okay, almost to the end. Next thing that we need to do is I want to be able to connect adjacent PCBs. So in this areas over here, I need to have a solder mask. Coming back to my recipe, I actually traversed the solder mask DXF twice. One of them for the front mask, one for the back. Coming back to the Python shell, run it again, and now we see that if we turn off two layers, I have these two solder mask areas. So front mask and bottom. So now I will have exposed copper in these triangles, and so on the top and the bottom layers. So when adjacent PCBs touch each other, they will be connected, and you can also have solder in between. Okay, so now the power grid is connected to all of the LEDs. They're able to connect to each other between the top and bottom layers. All the routing is done. The last thing that I need to do is to have the drill holes for actually bolting the adjacent PCBs of the ring light together, as well as here on the bottom in these triangle, this is where the actual wire connections would be. I don't actually need to make those connections on all of them because of the adjacency connection. So again, here in Fusion 360, I have a sketch here for mounting holes. And here I have 1, 2, 3, 4 holes for adjacent holes. Each of those are 3 millimeter diameter. Here I have an additional 3 millimeter diameter circle as well, in addition to 2.5 millimeter circles. The diameter here is actually not that significant as long as I have unique diameters for different purposes. I'll show you what I mean by that. Here, once again, I traverse DXF. My action in this case will be a mounting action. So for the mounting holes, and this mounting action takes as an argument this footprint mapping. The footprint mapping says whenever you find a circle with a 3 millimeter diameter, put this footprint in that place. So we're going to turn that on. So that will be for the left, right, and bottom holes. Then I will run that same mounting action again twice for each of the circles that are 2.5 millimeters and put a test point in that spot. And I will do that twice because I want one on the front and one on the back. For one of the runs, I will actually flip the modules so that it'll be on the back side of the board. Okay, so save again, back in the scripting window, and now we have our test points. And now we have our mounting holes here on the left and right. We have another hole here, which this is for connecting the ring light to some sort of a bracket. And additionally, underneath here, I have some pads. Now, I didn't tell it what those should be connected to, so I need to do that now. So go to properties here on the front pad. Here I want plus 12 volts. Do the same thing again for the back pad, plus 12 volts. Again here on the ground, edit footprint on the front, GND, edit again on the back, once again GND. Refill, and we'll see that now the power is connected to this pad as well as this ground pad. Looking on the bottom, the same is true there as well. So now I have an additional step of cleanup that I need to do here around these mounting areas. Because the via fill was already here, I need to remove these ground vias. And here then again on the right. So at this point I have what looks to be a completed design. I have all the LEDs where I want them. I have them connected to each other. I have them connected to power. I have some large power rails that connect from one PCB to the next. The boundary of the PCB itself is such that when I connect the 8 of them together, they'll make a nice circle. I have mounting points for bolting them together. I have a solder mask for being able to solder adjacent PCBs to each other. I have lots of vias for connecting the front and back parts of the power. And as you see, very little manual work was actually involved. And that was almost exclusively limited to deleting stuff. In upcoming videos, I will explain in more detail how these scripts work. Anyway, I hope that this gives you some ideas on things that you can do with design automation. Scripting in Python and PCBnew can be a very powerful tool. Some of the things that I did here, like the Delaunay triangulation and Steiner trees, may seem a little fancy, but even for things like just connecting the pads with grounds, it's very simple scripts. I hope you found it useful and interesting, and hopefully it will inspire you to put together some automation of your own.